Okay. All right. So, how's it going on? How have you been since the last time we met?
Busy.
I can imagine. Right.
Very busy.
All right. But were you able to somehow reflect on the class last time as you went through your week of teaching for those who are actively in the class? Were you able to, say, aha, here's one of those moments on what we, our introductory class last week? Anybody?
Well,
Yes, I think so.
Okay.
there's the Sunburn weekend there, so we haven't had any classes since last week.
Okay, that's you, Kamisha. Who just shared? Kamisha?
Yes,
Okay, okay. All right then. All right then. How about our friend?
that's me.
Uh, how about our
Yes, ma'am.
All right. How about our colleagues from Bermuda? Any other reflection since the last class on what we had discussed about this whole concept of who we are as teachers and how we treat our students?
I was reflecting on the quotes. You know the quotes I'm talking about?
Or there seems to be something not hearing you clearly there in Bermuda. Is that you, Ashley, or Tracy? Hello? Bermuda? Can you hear me? Oh, somebody's coming. Assist. Sounds very quiet. All right, we seem to be having a
Can
little.
you hear
Okay, I was
me
just.
now? Can you
Yes,
hear me now?
yes, yes.
Okay, I was just looking back at the quotes a lot. Can you hear me now? Can you hear
Yes,
me now?
yes, definitely.
Yes, we can.
And that's a cleaner sound. Thanks, Ashley.
Oh, okay, great. I was just reflecting on the quotes that we reviewed quite a bit, and just looking at them in like everyday life, like remembering what we had discussed first, and as I went through the next couple of days, I was kind of just reflecting back on those and how each day I could see the relevance of those quotes in each day a little bit here or there, one way or another.
Okay, okay, fine. These quotes were in the presentation or those quotes in PowerPoint presentation?
The quotes on Wednesday class for this class. My bad. My mistake.
Okay, okay, no problem. I mean, the important thing is that you see that whichever course we're doing, that we do that exactly that. Reflect on what we have been introduced to, interrogate, you can accept it. But as you said, everyday life as well as in the courses that you're doing. All right. Today we're going to be looking at the concept of the nature of science. The nature of science, not something that we hear being spoken of um, all the time, but I'm going to just carry us through a discussion on what is the nature of science, what is its relevance, and I'd send you the PowerPoint presentation. Have you all received this PowerPoint presentation?
No, you sent it? Did
Right.
you send it today?
Yes, apparently it was sent around noon today. All right, don't worry. I have it
Oh,
so I can share with
oh
you.
no. What is it?
All right.
I'll try and get it.
I'm going to share my screen with you. All right. Can you see the screen? Is it clear enough?
Yes, we can.
All right. Okay.
Very clear.
All right. That's great. That's great. So this is what we want to look at today. We want to know, how do students view science in your classroom? What are your own personal views on the nature of science? And then, why are we even doing this? What is the impact of teachers' views on the teaching of science? And we have some articles that we're going to kind of quickly review. And then finally, can we as teachers effectively introduce this into the curriculum? I remember last week, Samuel was a little concerned when I was suggesting that, and it's a concern for all. I just remembering Samuel. If we are to explore anything else,
Okay.
yes, Samuel, I'm not picking on you again. But if we are to infuse this thing that we're going to be looking at called the nature of science, how is it that we are going to, what impact is it going to have, one, on the teaching of science, and how are we going to bring it into our classroom? But the first thing I want to know is, for yourselves, what are your own views on this thing called the nature of science? I'm not even going to go into what it is. What does it mean to you all? And you have choices here today. You can choose any one of those methods to kind of depict your view on what you think are the characteristics or the features or what we call the nature of science. You can draw something, you can write a poem, you can put a rap together for those who are more inclined that way. Just or narrative or a monologue, just something that for you says, this is
Do you
how
have
I would.
handouts and stuff?
Let's give you a few minutes to just.
No, I'm asking a question. Do you have the
Everybody got that?
Yes.
Yes.
Not putting you on the spot. It's your choice. So, as I said, you can make a drawing, something to depict what science means to you. What is science? When Jason was doing his biology degree, what did it mean to him? For you, Tracy, you're there? All right. So I know you're the biochem person. So what does science mean to you? And maybe as a lab technician, it has brought on brand new meaning for you. Same thing for you, Vanessa. Genetics was your specialty or is your specialty. What does science mean to you? So choose any of those. Kamisha, Samuel, Ava. Choose any of those options. If you're not an artist, don't worry about it. Just write something to express. All right. So let's see what we can create in the
Okay.
next 5 minutes. Of course, be prepared to share, right? You know how this thing works.
Okay.
All right. And even though this is not a methods class, I like to model things so that you can have an idea of what you can do with your own students. You know what I mean? I know that you all have this down pat, but sometimes when you see it in action, it reminds us of, yeah, I could do that with my class. So this is not a methods course, I know, but just encouraging you that you can do little things like these, with your students.
Oh my gosh, I need that.
Yes.
Hello?
Yes, go ahead.
St. Lucia, we have a new student here. I'm not sure if you have him on your list.
What's his name?
You can go ahead. Linton what?
Linton Alphonse.
Oh,
Linton Alphonse. It's first day, so I'm not sure.
okay, yes, his name has been on the register. You're with us now today, Linton?
Yes, he has arrived.
Okay, welcome, welcome. I'm not seeing you though.
Maybe I should come across.
Yeah, you can come across. You'll come across just now.
All right, good.
Okay, let me get back into the mood. So is it only the 12 doing science?
No, I have somebody else.
So 3.
3 or 4.
Okay, so now I'm kind of new to the system, so
You just go ahead, and she wants like 5 minutes or so to choose any of the following and just write something on it in terms of your own view with nature.
I have my 5.
You write it, you can write it on the paper, I guess, and then you just share it.
But no Wi-Fi, no internet.
Yeah, you have Wi-Fi here.
That's the box.
Password,
Yeah.
do not forget.
Linton, at an appropriate time, I'll just have you introduce yourself to everyone. And, I'll
Okay.
also introduce myself.
Okay.
All right.
So are you ready now?
Let me just allow
I think you have to do that.
the creative juices of the others. I don't want to interrupt them too much right now.
Okay.
The task that we're doing is just asking persons to just write their own views. What does the nature of science mean to you? What do you think when you think of the science, whatever your specialty is? How would you capture your philosophy of science, whether in a picture or a poem, maybe a song or a rap, maybe a monologue, just a short thing, just to capture what science means to you.
Okay.
All right. Okay. I can see that some persons are well into this. They've reached their second stanza. Just joking, just joking. That's 2 more minutes, and then we just ask persons to just share. As I said, it doesn't have to be something long. All right.
All right.
Okay, that person sounds like they're raring to go. All right. So, without me necessarily firing away at someone, would someone like to volunteer just to share first off, and then everybody else will share their own view. What is this nature of science? What are the characteristics of science? Go ahead. I see Ava dying to go.
You can say, okay. I guess when you go first, nobody remembers what you said.
Sorry, go again?
Can you hear me?
Yes, I hear you now. Right.
Okay. What does science mean to me? Science is
No, sorry, I'm losing you here. Sorry. You're breaking up there. I didn't get that at all. After you said what's that?
uncovering the covered.
That at all. Are the others hearing it now?
Yeah.
Yeah.
Everybody?
Hi there.
Yes.
Yes.
Dominica, you're hearing Ava?
Yes, we can.
Clearly.
Okay, all right then.
Okay.
Go ahead, Ava. Yes, you're
I'll
on.
go Science is uncovering the covered. If ever you are a thinker, science is never really factual. Science is real and imaginative, sorry. It's creative and subjective. So if you seek knowledge, come to my college, science.
Ah, hi. All right, thank you very much.
Yeah.
Applause, man.
That's very good.
Went deep end there. Okay, thank you. All right, well, Linton, I know you joined us last. I won't pick on you just yet. Anyone else would like to share? Next.
Okay, Samuel from Dominica.
All right.
But I have a picture to show. I'm going to show everybody.
Okay. Samuel.
This is my picture. This is a piece of chalk.
A chalk.
Yes.
A stick
For
of
writing.
chalk. All right.
Yes. Okay. Chalk is from acid. It's a salt from acid called carbonic acid, and is
I think so. That's it for
Sorry, Samuel, are you speaking? I'm not hearing you after carbonic acid.
okay. I said a piece of chalk that we use to write carbonic acid.
Right.
So chalk is called calcium carbonate. And also, to me, I can say chemistry is about relating everyday life, what we see, to its origin. So I think some student teachers are not aware that the chalk we use is calcium carbonate.
Sorry, Samuel, you keep going in and out, so I'm not getting the full essence of what you're sharing. I'm not quite sure why your voice dips. Are the others hearing Samuel clearly, Bermuda? So it's my end. St. Lucia, you're hearing Samuel clearly too?
in and out.
In and out. Yes, I keep hearing his voice in and out. Samuel, can you hear me clearly?
Yes.
All right, let's take it from the top again, Samuel.
What did you say?
Let's take it from the top again.
Okay. I said this is a piece of chalk.
Right.
I said chalk is from acid called carbonic acid.
Right.
And the chemical name for chalk is calcium carbonate, which is salt. And I said that chemistry is about relating everyday life, what we use time. Everything has a chemical name from where they come from.
Okay. All right. So you're more.
So
That's science for you. It's really the infusion in everyday life.
yes, to its origin.
Okay. All right. Kamisha, how about you? Well, it seems as if Kamisha is having hers.
No, I have something. But what's the name? The one from St. Lucia.
Ava or Linton?
Ava. That's okay. That's okay. Go ahead.
I have this food. Science plays a role in all we do. Why? Because science is life.
Okay.
Very nice.
Thank you. All right. All right. Good support there. Glad that you're supporting your colleagues. All right. Now over to Bermuda. Who'd like to go? Kamisha's still at it. Who'd like to go first? Vanessa?
I'd like to go. I think mine follows along with hers.
Okay.
think science, science is about everything that is living, and when used correctly with good conscience, science can improve the well-being of all living creatures.
Okay. Thank you. Next person.
I wrote a little poem. Ashley from Bermuda here.
Yes, yes. Uh-huh.
I said, science is the fundamental of things. Even art, music, and the way we sing. The things you wear on your fingers, a ring, can all be depicted in this essence. The presence, credence can stem from, you know them, proton, I'm sorry. The presence, credence can stem from the nature of science. You know them? Protons, neutrons, electrons to take and explore.
Okay. Thank you. All right. So, all right. If you notice that there's a general theme ringing through everyone's presentation, but we'll come back to that. All right. So I heard from Vanessa, Ashley, Jason. Oh, we should let the young lady go before. So Tracy.
That was Tracy. Tracy did hers already.
Oh, so Vanessa, I'm inviting you now.
I've actually got something for Samuel as well. My chemistry teacher used to have a poster up in the lab saying, "What in the world isn't chemistry?"
Okay.
Mine is actually a picture as well, and I'm just going to describe it because it's really badly drawn stickman.
Okay.
I am so bad at drawing, but I'm worse at writing. It's a man with question marks all around his head. He then does an experiment, comes up with some data. I've got a graph. Happy smiley man, because he now knows the answer to whatever his question was, which he can explain to other people. So the last one is him talking to a room full of people.
All right. Okay, so his questions get answered. All right, so Jason, you're the penultimate person, because Linton, you're not off the hook.
Okay, no problem.
Just forget me.
I actually did two things, but I'll just say one. And I guess the first one was a picture. And I drew a water droplet because for me, science is a means to help people in economically less developed countries to have clean water to drink and have sanitation. I guess that's more of a personal thing, but that's that's
All right, let me see. I heard here you drew a water droplet.
yes,
All right, and that depicts really how science can help others.
yes, basically to improve their quality of life.
Right, improve quality of life. Okay, okay, okay. All right. Thank you. So, Linton, you get to carry us home now.
Okay. All right. I just have a little jingle. I'm kind of science is fun. Science is an engagement. Science is everything in our environment. Science is the talk around the world. We love the scientists. Science brings along investigations.
Okay, all right. Thank you. Let's give him a hand too now.
Oh, sorry.
All right. Now, this, as simple as it was, it really, a simple exercise that is, simple in terms of, I guess, me issuing the exercise. Maybe it wasn't so simple on your end to have to come up with what you did. But it really will help us to understand how we view science and how we value science. And we want to look at some research work to see if how we view science influences how we teach science. Because we can have a view of science, but it doesn't come out in our teaching, in one way or another. So I can, for example, think that for science, students really need to be active. They need to have hands-on. But I can be so concerned, like Ava, in a way, or was it Samuel, the curriculum sometimes bind our hands and we don't get to really infuse what view we have of science, being hands-on, as in my case, because I have to get the content, so to speak. I might find myself being content driven, but we want to definitely look at how our views influence our teaching, and if in fact they. Sorry.
So we're supposed to attend class Wednesdays. What is this?
Sorry, someone is saying something.
No, sorry, no. Go ahead.
Oh, okay, okay. All right then. So, the nature of science. Most persons tend to look at the nature of science as the scientific method. And this is a cartoon clip that I thought that was kind of, illustrating what I was saying. So here we say the scientific method, the way of exploring, investigating, coming up with new answers, problem solving. But yet, here we see persons who sometimes might be the movers and shakers behind, science. Our hands are tied. Here it says you're completely free to carry whatever research you want, so long as you come up to these conclusions. So even for ourselves, we might be saying that we want science to be infused in everyday life. We want science to improve the well-being of others. We can see it acting out in our everyday life. But sometimes when it comes to teaching science, our hands are tied by various different things. In this case, it's someone who's providing the money for funding a particular project, and that certainly happens in the States and elsewhere a lot. But we want to recognize that even for ourselves as teachers, that we aren't so free after all to carry out what we think is our view of science. All right, so what is this nature of science? Here's a very convoluted expression. I'll give you a few minutes to absorb that one.
Did you get that email?
Yeah, it's supposed to be in your thing.
Yeah, I got it.
That's what I was wondering, but I didn't want to like do it and
We wouldn't blame you, Jason.
Just take you out, beat you, it's fine.
Oh,
All right. So the epistemology of science. Science as a way of knowing, or the values and beliefs inherent to scientific knowledge and how that knowledge is developed. That sounds really convoluted. Here's another way. It is a study of scientific knowledge, but not just the study of the knowledge. It's presuppositions, foundations, validity, methods, limits, justified beliefs. The nature of science is not about, if you look at it, it's not about just the content. It's about the how. It's the, as it says in the first one, the values and beliefs that are inherent. You shared your own values and beliefs about how you think science should be taught or should be communicated. That itself is the nature or some of the characteristics or features of science. What do you think about these two expressions about the nature of science? Let me go back to the second one. The first one, where is it? Okay. So it's science as a way of knowing, values and beliefs. And we're going to look deeply at our own values and beliefs, and interestingly enough, our students' values and beliefs. All right. So let's be honest. What do your students think about science? I think of the picture that Tracy said she had drawn. With all the question signs around. I remember I had this clip, this cartoon clip. But what do you think your students think about science? I want a really agitated, or rather animated discussion here now on this one.
Okay, well, generally they think when you do the sciences, like the picture says, you sit in the lab and you mix chemicals and that's about it. You cut open frogs, you look at this, you do this type of that. They really think that science is mainly hands-on.
Okay.
And not much theory is put into it. Well, that's what they think.
Right. Okay. Anybody else?
Yes.
Just introduce yourself as you're meant to speak so that, you know.
Okay, Samuel Dominica.
And this is Camisha Dominica.
Okay.
Okay, Samuel Dominica. I think my students, most of the time, they think of what can they mix to get something that has not been done before.
Okay.
So they always think of science like, oh, how much can they put together to surprise everybody or to surprise themselves? I say to make a bomb.
Especially to make a bomb. Right. They want the cool stuff, right? They want the excitement.
Yes, you're right.
Fine, fine. Anybody else?
Students,
Tracy? Let's ask Tracy as a lab technician. What do you think the students think about science as you provide that kind of technical support, you know, to your classes?
At the school I work at, the kids love science up until year 9, and then we tend to lose them. I don't know why we lose them. We still do a lot of experiments, but I think there's more focus on the technical parts as opposed to the experiments. The experiments, we love the experiments.
Okay, they love the experiments, but what do you think is a barrier to them really enjoying it as they did up to grade 9?
I think if it's more curriculum, you really do have to follow the curriculum more strictly
Right.
because it's not do the K3 and we have leeway. And we have them more often. So you can step outside the curriculum that's set. You
Right.
can do field which isn't in the curriculum, but then once you get up in years, it's pressure to get
25th.
25th of February.
And what exams are they being prepared for in 4th and 5th form, or grade 10 and 11? What exams?
For the younger ones, we just in-house exams.
Right.
And then the older ones, we do IGCSE and then IB diploma.
Ah, okay. All right. And again, we've seen another trend, which we're going to look at shortly. How the curriculum does tie our ability to really explore fully this concept of the nature of science. Ava, Linton, how about you? Linton, let me just introduce you now. Let's give you a chance. This is now your time to be introduced. Just tell us your full name, your discipline, and if you're actively teaching now on what school. And we all say hi back.
Okay, no problem. All right, well, my name is Linton Alphonse. Actually, I'm an agricultural engineer, and I teach at the Viewfort Comprehensive Secondary School. For now, it's 9 years since I'm a teacher there.
Okay, all right. Thank you. All right, so welcome again. So what do you think your students think about what you teach? Think about the science in itself.
Okay, well, basically, they see science as something that is hands-on, something that they always want to invent. They're curious to find out what things are, what's the purpose of certain things. So most times when you do something like experiments, they're very observant. And in terms of writing, they have difficulties in like reporting.
Okay, right. But making the observations and having the dialogue, they're okay with that.
Yes, they're okay with that, and they're curious to see more things to happen.
Right. Okay. Well, this thing, I think it was, let me see who spoke, who shared first. I think it was Ava. Ava had shared in the opening activity about the nature of science, how she viewed science. And she mentioned, I think, some of these about it being creative. Am I correct, Ava? About the real and imaginative, was it you?
Yes.
Right. And
Yes.
okay. Now these points, can everyone see them clearly?
Yes.
Yes.
Because I actually it's a what do you call it now, a print screen that I just copy and paste. So I wasn't sure if you were able to see it clearly. But these 7 aspects of the nature of science, they are part of what we call the characteristics of science. So tentativeness. What do we understand that term to mean? That the nature of science or science is tentative. Anybody?
Only for a while.
It's come again?
Only for a while. Only last forever.
I like that one.
Only for a while.
Yes, I like that one. Only for a while. I mean, today's theory can be knocked down, in 10 years' time. So you're right. It's tentative, lasting only for as long as it remains true until something else knocks it out. Creativity, creative. Is science creative?
Yes.
Most definitely, continuously so. Observation versus inference. This is something that I'm having my students, I'm having a challenge for them to make the distinction. Seems pretty obvious to me, but I don't know, is anybody else having that difficulty where students sometimes do not really see or are able to express these things differently?
I think so. I think even science teachers probably have problems with it.
Right. So let's try and flesh it out here then. Observation versus an inference. What are we referring to? Let me bring someone in on this. Ashley? Oh, not yes, Ashley. What's the distinguishing feature between observation and an inference?
Let me see. I guess observation is something that you stand by and watch while the other is making it happen yourself and like discovering it as you go along.
Discovering it. Discovering it. All right. Discovering it based on what you have seen.
Yeah.
All right, Vanessa. What do you say about that?
I would say an observation is something that you are actually, like a measurement that you are taking. An inference is something you can deduce from that observation.
From that same observation,
What
right?
that observation means.
What that means.
Yes.
Right. Because, and that observation, as you're rightly saying, both yourself and Ashley, is that it can be something seen, it can be something that is detected by any of our senses, really. But having made that observation, what does it mean? What does it mean? Where am I going with it now that I've made this observation? And I find students sometimes are not very clear on this. And the whole point of this lesson today is that we don't teach our students what the nature of science is. And when we don't teach us, we don't know what it is ourselves. We aren't clear as teachers, and we are not communicating it to our students. And when we see that our students are not making certain distinctions in our practicals, in writing up the labs, as Linton said earlier, we wonder, why can't they get it? Why aren't they seeing, these fine features of what we know or appreciate to be the things that are just a part and parcel of science itself? If we're not deliberate, if we're not explicit in teaching what the nature of science is, what the characteristics of science is, or the characteristics are, then we find that there are going to be gaps in their thinking about science. And so they become very, what I call 1, 2, 3, very literal about science, not really exploring these things, not bearing these things in mind. Subjectivity. Science, the students, if they get a result, they can't appreciate that result is not the end all, having done a lab or an experiment. They don't recognize that it's subject to interpretation, even the very inference. Both persons can make the same observation, but they have different inference. You agree?
Yeah.
Agree.
Right. So science is subjective. Another aspect or nature of science is the functions and the relationships of theory and law. They're distinct things. Theories are totally different from laws. You have Boyle's law. Am I correct, Mr. The chemist among us? I'm a very poor chemist. Right? Boyle's is chemistry, right? Or is it physics?
Both in chemistry and physics.
Okay.
Yeah, I guess technician enough to ask.
And so they need to appreciate that there are theories, for example, the theory of mass flow in plants for the movement of food. But someone can easily come and knock down that theory. Am I correct?
Yes, you're right.
Right. But laws, empirical laws should have been proven, and we can accept those are not really subject to massive changes, maybe amendments, but not massive changes. Another thing that we rarely ever teach or even appreciate ourselves, and that's the main thing that this course wants to focus on, is that the one aspect of the science is that it's socially and culturally embedded. That culture, or your own cultural background influences how you teach science. How my own cultural background and social, socialization influences how I appreciate science and how I in turn teach science. And then finally, I think this aspect we drill into their heads that science is empirically based. I don't think any students of science will miss this point. That is based on empirical evidence. That what is the evidence to support your claim? I think we teach that very well. But the challenge that we have as teachers is we want to be able to, all these characteristics or features of science, can we truly embed them or infuse them in our teaching? And frankly speaking, should we even consider doing so? All right. Now, there are some, let me do this, let's see now, from current slide. There are some researchers who, it was a 185-page document, and I thought I would not try and send that to you by email because you would all quit the program immediately. So I picked out, the things that were salient to our discussion. But it's a group of researchers, Driver and others, who dug literally into what young people thought of science, and they dug into various aspects. They picked out three main areas, but I looked at three main areas. The book is a book, all right, so it's 185 pages, I can imagine. But they looked at how students saw the resolution of conflicts, how they viewed the interpretation of any scientific evidence, and and how they thought that there were any disagreement in science was resolved. Now, why is this important? Think about students doing a lab, and the results that they get doesn't seem to conform to the expected results of theory. What do students normally do when this happens?
They shut down.
They look for a flaw in their measurements of the study. Like if they're doing a chemical reaction or something, and they're trying to figure out how hot or how much, when you add this to that, how hot it's going to become, and the reaction becomes 10 times hotter than it should have. So they go back to their fundamental preliminary whatever setup to
Right.
see if everything was, in accordance.
Fine. And that's good. That's a good approach. So that looking at their methods to see, did we do something wrong? So that's good. First base. What else do they do? Let's say that they found out that the steps were correct, the sequence was correct, they made whatever chemical reactions, whatever reagents that were to be used, they were correct. Let's say that they've done the method correctly. What next do they tend to do?
My average student will shut down and give up. They would figure they did everything, it didn't work, and that's it.
All right. Anybody else in support of that statement? Well, let me put my hand up. That's what I do. I've had that experience. They think that there isn't anything, there's no more thought process to what could be going on. Right. Anything else that they sometimes resort to doing?
Falsifying the results.
Ah, yes. That was you, Jason?
Yeah, but I think it came from Vanessa or Tracy. I'm not sure.
Sorry?
I just said it.
And the school, if they don't get the right results, they take it from someone sitting across the bench.
Right. And everything I said to us.
Thank you.
I'm hearing some disturbance. I'm not quite sure where it's coming from. Okay, all right then, good. Thanks. Right, can you hear me?
Yes.
Yes, we can.
Good, good. And in Jamaica, we call them cookbooks, where students will get, if the experiments are basically the same from year to year, they'll get a cookbook which has kind of the experiments with the expected results, and they would have that on the reserve just in case their results don't conform to what they think they should have received. And, so they consult their cookbook, or, as was said by Tracy, that they will just take the results from somebody else. But what do you think that habit will do? What do you think that will do to our young scientists' minds?
I don't think they would be creative. They would just be looking for the correct answer and not discover anything new. In terms of the development, cognitive development stuff, they'll just be at one level because you already know the expected results. So you'll be working towards that result without having any kind of new discovery or anything of that sort.
Exactly, exactly. And remember, we said one of the features of science is that it's creative. That yes, it's tentative, but it's creative. And if students keep on, as was shared earlier, shutting down or they falsify information, then they might have actually come upon something that has never been thought of or something new, but because they think that it's not in keeping with the expected results, that it's shut down. And we as teachers need to ensure that we help to promote that creativity, that we help them to explain why something didn't work, why the results were not up to, try to troubleshoot why it is that the results weren't as expected. Because as Ava shared, if we keep on thinking that it must be one way or it must be this accurate, correct way without even at least trying to provide some kind of explanation, we're going to shut down their creativity. We're going to shut down the the enterprise of science, where, as was shared by several of your colleagues, that it is something to improve the well-being of life, of all living creatures, Vanessa had said, and Jason had said, helping others to improve their quality of life. If we're not careful, if we shut them down, then say, oh no, that's not correct. No, that's incorrect. I'm not saying that we can't say something isn't right, but especially when it comes to exploring something and doing an experiment, ask them to try and figure it out. Help them, act as a scaffold to bring them to interpreting their observation. Remember, that was one of the features of science. All right. How do they view the interpretation of science? Well, we kind of touched on that they think that something might be wrong, that they will try and do something, to try and overcome what they have seen, or they don't even try and give an interpretation at all. So this group of people, Driver, picked out these three things among young people, and then they did an intervention, asked questions, and these were some of the things that they came up with from these students that they had done the research on. So for the first one, how do students conflicts, the formation of scientific knowledge? These were some of the comments that students made. That scientists have different views or ideas. Everyone will never agree. New information is not to be trusted. So they had a view that scientists will never, sometimes the differences in knowledge is because of personal conflict, that scientists will never agree because they're people and people don't always agree. For the second one, how do they view the interpretation of science? They believe, students that is, or young people, that proof comes from the presentation of facts, that scientists never admit wrong. And I found this, that they don't think that there is room for where there can be something else. It's either wrong or right. And so Driver and others, in their research in 1996, when they produced this, found that students thought that, you know what, scientists never admit wrong. And as a result, when they did their experiments and it didn't come up quite the way the scientists or the proven theory or laws suggest it should be, then they will shut their own minds and never put forward their own view. Everybody following this so far?
Yes,
Yes.
yes.
So in other words, somehow, somewhere along the line, how we have been teaching science has caused us to, even though we have this understanding about the nature of science being creative, that there is observation versus inference, that it's tentative, that, as you said, here today, gone tomorrow. Even though we have that view of science, that it should be in our everyday life, it should help people. Our young people don't seem to be getting that at all. Our young people are not getting that kind of image of science. They see science as something that there's no new information, there's nothing new to add to the already existing body of knowledge, that scientists, fact is fact, and anything else that comes up must line up with that fact, and that scientists never admit wrong. And you know where they get these images from? Where do you think they get these images of science from?
The teachers.
Their teachers.
Yep, from me. They get it. They get it from us. They get it from us. And this is the conflict. How can we have such a clear understanding of what science should be? Yet when we're teaching our biology, we drop it. When we teach our physics or chemistry, agricultural science or biochemistry, we don't bring it in. And we want to look at that. We want to examine ourselves. And finally, they said, how do students socially account for disagreements and resolution? They think that money, the person with the money or the big bucks, that they're the ones who determine what the final, say is, and that moral issues can be compromised. In other words, just as Samuel had said, some of them will falsify the information, and we have seen that for sure. And even by what Tracy had suggested, that they're plagiarizing, just borrow somebody else's results. All of these things we need to look out for. We see it happening, but we need to examine how do we as teachers address it? Should we address it? Do you think we should address it? Let me throw that one out. Do you think it matters? This was in 1996 and we're in 2015 and it's still going on. Should it be our concern? Sorry, go ahead.
Kamisha from Dominica.
Yes.
I would say that we could try addressing it, but there's only so much that we can do. For example, Mr. OY, Samuel and myself are doing this class and we're learning something. But Dominica has how many hundreds of teachers? So the two of us may be able to work with our students, but then what happens to other students, and they may become teachers, and the same cycle may continue.
Right. What about our colleagues from Bermuda? Do you think that this is really a big deal? Should we even be having this conversation about who cares what students think about science?
It helps us to look forward to seeing trends in our students to help move toward understanding more, or the trends help us to understand. Having the information helps us to understand what we can do to help the kids, help the students. I guess.
Right. Okay. And Lucian? Should this be a concern of yours? Do you see this being of any use and relevance to when you're teaching your students your hands-on agricultural sciences?
Go ahead, Linton. Go ahead. I'll give Linton a chance. I think so, yes. Yes. But I'm thinking, maybe I can be wrong, that teachers were also taught by somebody. So it's let me put it right. it may be a continuity of bad practices or something, because you learn that unless you're not self-motivated and you're not willing to change, you don't want to have a like you want to have, if you have a want to have a paradigm shift in something that is different, you yourself have to have that intrinsic need to change and say, and be a scientist yourself. Even though you were trained a certain way, you have to probably deviate from what you were taught and then go and teach in a different way. Because generally, I read that students um, today, to me, they are bored. They are bored in terms of science. They see science as something that is boring. I'm not saying all the sciences because it might be different depending if it's chemistry, physics, or agricultural science. I might be able to impart some kind of life into it, fun and active themselves on the farm whole day. But for other persons, they might not be able to do that. You have to go into a lab and do other things that might not necessarily be part of the curriculum. But I deviate. That's okay. And so you tend to teach how you were taught.
Right.
So if you're not taught the right things, I'm guessing that you might continue that without even really knowing that you're doing a disservice to your students.
Right. Very, very good point. Very good point. Very good point indeed. Because the truth is, I note what Tracy said earlier. She said at her school, and I think we could almost all agree to some extent, at the school that we teach, that students are really enthusiastic up to grade 9. But once we hit the 4th, 5th form years, where they have to now be prepared for an external exam, all the excitement that they had kind of starts to wane. And because there's this curriculum, there's this very narrow curriculum, so to speak, very prescribed, not as open. Most schools create their own curriculum 1st to 3rd form, something that they have modified. Yes, there might be something from the Ministry of Education or wherever you get your curriculum from, but there's always room. It's flexible, and usually because the teachers know what the students from their experience know what they have been exposed to, what works, what doesn't work. Teachers over time tweak the 1st to 3rd form curricula just to meet the needs of their students, and it's an internal exam. But once we hit the 4th, 5th form years, and we're now preparing them for an external exam, we tend to become so much more content driven, and we want to be aware that that's not enough. We're going to lose the students. And as you correctly said, Eva, they become bored because they're asking, where's the relevance of this? They don't seem to see how science can work for them, and we have to provide that. All right, so let's flip the coin a bit. There was another research. Lederman, that's the author. He looks on the views of teachers on this same thing that we've been talking about, how teachers view the nature of science. And basically, just to give you, I think I sent the article, but I know you wouldn't have had time to read it. So again, I just picked out some of the key things. That when they interview teachers, just like I had done at the very beginning of this of our class today, when teachers were interviewed, they expressed the nature of science, what it is that they would like their students to be doing, what it is that they want their students to achieve, how they would teach their class. Really exciting stuff. They picked out things that they want the students to enjoy science. They want it to be dynamic. They want it to be creative. They want the students to be able to think on their own, to be critical thinkers. Wonderful things. But guess what? Letterman, and when they did this in the late 90s, they found that as much as teachers were expressing this view that this is how I want my class to be conducted, they said teachers rarely considered that very same thing that they wanted, the creativity, being able to explore and for students to have a voice in the classroom, that they rarely plan for instruction for the nature of science. So it says teachers rarely consider the nature of science when planning for instruction or making instructional decisions. they didn't deliberately teach the nature of science. They didn't, it was just by the way. And they found that teachers who were new or young in the business were more concerned about behavioral management, classroom behavior management. They were more concerned about ensuring that the content was accurate and correct. So the second point here says teachers' beliefs on the nature of science did not necessarily reflect their classroom practice, especially for inexperienced teachers. So let's flesh this out a little bit more. So they're saying that as much as teachers had a viewpoint, let me go back to that about, let's see, I picked it up from somewhere. Here we go. As much as teachers generally felt that science was tentative, creative, that you need to teach them what's the difference between observing and making an inference, to teach them that it's subjective, so their results, once they get those results, they're not to discard them, they're to just try and find a way to explain them in light of the theory, all of these things. That as much as teachers were aware of this, to some extent, not all, that they were not deliberately, they were not planning for it. In other words, it was never in their lesson plans. In your lesson plans, how we tend to put social skills or we put cooperative learning skills. What are some of the things you put in your lesson plans? Apart from the content, what are some of the things that you add to your lesson plans that you want your students to be able to accomplish, over a period of time, over a unit of work that they're doing? Anybody at all?
Okay, Samuel, Dominica?
Yes, Sam.
Yes, what I normally make sure the method that I want to use.
Right.
The questioning method, the demonstration, and the video to support my lesson plan.
All right. Okay. All right. So the methodology is very important. Then your material. All right. Anybody else? What else do you put in your lesson plan? What do you think about? That's what it's talking about when it says planning for instruction, your lesson plans. Anybody writes lesson plans?
Yes, activities maybe.
All right.
What else do you do? You're trying to get rid of the evaluation.
Okay. Well, what do you want to achieve?
Prerequisite knowledge, practice.
Sorry. Go ahead. Prerequisite knowledge.
Yes, etc., etc.
All right. Fine. We know the points, the headings. But what do you want to achieve? What are some of the things you want to achieve from your lessons or to build in your students? I'm not necessarily talking about that they must now be able to, know how to apply, quantity of fertilizer to a plot of whatever, or they must know. Yeah, you hear the skimpiness of my agricultural knowledge, right?
Yeah.
Right.
Noted.
Right. So it's not about the
Samuel, Dominica?
but the skills. What skills do you want them to have? Go ahead. You see, this is very
Silent zone.
Speaking. Sorry.
Yeah. Anyhow, can I speak?
Sure.
You would hope, for me, I would hope that they would use the content or the knowledge that they have gained and do a transference, like a follow-up. Like you have a lesson, they would use that knowledge that they gain to maybe better understand the next lesson, because it's supposed to be like a follow-through. You follow in a trend of thought, you teach them something, and then the next day you go back, you do probably a preview, and then you move on. So you must make that link.
Right.
Between what you in the classroom and maybe when they go outside, and not only in the classroom, but the wider society. When they go home, they might be able to know, okay, the water, if I mix water and some other chemical, I'll get that, and I'll see diffusion and simulation and all these kind of things. So you must actually have to tie in the classroom experience to with real life experiences that they can actually relate to, not in isolation. So you hope that they can have a whatever moments, aha moments.
Right, right. Okay, all right. Anybody else? I'm still trying to get the skills. All right. So that was really the ability to transfer knowledge, to apply. All right. Any other skills that we want our students to have, regardless of what you are teaching? Because
Okay, Samuel Dominica.
uh
Yes, I normally make sure that I start from what they know
okay,
and to always let them know that they have the knowledge of something already. So it's not for me to relate it to what I'm teaching and to go in depth more. But already I always let them know that they have the knowledge of what the topic or what I'm about to teach. It's not for me to relate it to what I want to teach them, but I'll start from what they know already.
okay, fine, and that's important so that it becomes relevant so that they can hear what you're saying next. All right. So what do you think now about this idea that we need to plan, infuse the nature of science into your lessons? Let's look at a video. I think there's a video on this. And tell me what you think of what the gentleman is saying. I hope you don't fall asleep. His accent is very, very American, I think, or British, I'm not quite sure. But let's view this because we need to understand if we're still making a big deal or how we view the characteristics and the features of science. How does it affect how we teach? So let's see if we can, oops.
Excuse me.
All right. You can see it? Sorry, that was what I was saying. Um, mhm. Where is it now? Can you see the screen? There they go.
Yes, we can.
All right, all right. You can tell me if you can hear as well.
Yeah, I have a question.
Yes, go ahead.
Before you start the film, I was just wondering, like, you've got these 7 aspects that we've just been discussing. Could you not discuss that with your students, like, when you get them in year 7 in a modified version, so that you're giving them a heads up of what you're infusing into your lessons?
Well, that's what I was trying to find out if persons do this. Do we do this?
I've never seen it done.
I love her honesty. And the question then, Tracy, is it important? Do you think this is important?
Yes.
So why is this that no one told us this?
I'm wondering that myself. We get our year 6s before they come to secondary, and we have them for a whole day, and we get them to draw what a scientist looks like and do fun experiments, but we don't say anything of what's the 7 aspects of the nature of science.
Or even 3 or 4, even if we didn't touch all 7, Is there any change in the curriculum, for anybody that you're aware of in your own countries that has tried to address this? And let me explain why I bring that question up. And thank you very much, Tracy, for asking that, because here, I think at the first form, if I'm not mistaken, we also teach something about our scientists. I think we talk about the Jamaican scientists. But all we do is there's a book that has been compiled that speaks of persons who have more or less, because of their work, they have this recognition as a Jamaican scientist. So it will tell you about kind of a biography. That's it. But but in terms of how they did their work, you know, the mistakes they made, the conversations they had, you know, it's the person in collaboration with other persons. That doesn't get, you know, that doesn't come out at all. It doesn't tell you how they made mistakes or they had to do an experiment 30 times or nothing like that. It makes it look as if the science is all clean and it has been, you know, that's how it is from the beginning to the end. What do you think about that? I've lost it. Are you there?
Yes, we are.
Did I speak too fast?
No. Okay, well, in Dominica, the between first story and third form, they have to do different activities in preparation for the PSLC. And one of the activities that they're supposed to do is to look at scientists in the Caribbean and basically give a bibliography like what you just explained. But something that I've realized is that a number of the students find it boring. So what they will do, they go on Google, type in the name, copy, paste, and they bring that for you. Because it really doesn't tell them to, you know,
Right.
delve into the lives of the scientists and you know that kind of thing. So they just do the basic thing to get the grade and that's it.
Interesting. Because even as Tracy said, these things could easily be addressed. And the video that we're going to look at is going to examine just how, you know, a way to consider infusing the nature of science in what we do, what we teach. Because can you imagine, I'm starting a course. I'm going to teach on, let's say, transpiration. I'm a biology teacher. So we're going to look at the rate at which water is lost from plants. And I can, you know, say that as much as we're going to examine these three different plants in these different conditions, it is possible that one plant might lose more water than the other, although we didn't expect it, And this means that science is, you know, we have to look at, make an observation, but we have to look at how we make an inference from that observation, I mean, I could easily be just simply be teaching point 3 right there. And I'm sure we can all come up with ideas of how we can infuse the nature of science, which we're going to do in a little while in our classes. But it's a very important question that Tracy has put forward. Where was this? Why is this important? Why is this coming up now? And it is true. It does have an important bearing on our classes. It's very important in science for students to know this so that each time a new topic is coming, they have this openness of mind. They recognize and they can interrogate what we're giving them rather, that's why they find it boring, Ava. Rather than just simply content, learn this, learn that, they never get the inside story. They never hear behind the scenes what's going on. But tell me what you think. Oh, sorry. So, Tracy, was there anything else you wanted to add or to comment on? Or anybody else, based on what Tracy said? Tracy's really challenging all of us here. Where is this coming from? Why is this coming up now? And how do we handle this new information?
Well, I think one of the issues with presenting this to a class is that our classes now are so curriculum based. You have to finish ABC within a particular time, that you do not have time to, how should I say it? I don't want to say it and it sounds bad, but sometimes you don't have the time to really delve into certain areas that will really grasp the interest of the students and will help them to love science more. We just basically have time to go to class, say transpiration is this, transpiration occurs in plants, you know, these are the factors that will affect the rate of transpiration, and that's the end of class. Next topic.
Ouch.
So I think that's one of the factors that will affect.
Right. Anybody has anything to say? Jason, what do you think about that?
I mean, I think it's important to cover these things because it's important for people to understand what they're involved in. I mean, but I think that's significant, like what she said about sticking to the curriculum. But I mean, I don't have teaching experience like she does or you do, so I can't really say. But I mean, based on your example of transpiration, that's, I mean, you put it in there. You know, you're still talking about transpiration or whatever, but you managed to bring that aspect out about observation versus inference. So, I mean, I would think it could be done. I don't know.
Okay, anybody else? What do you think? Do you think that, yes, we have the curriculum, but is there any way that we can possibly, not necessarily a whole lesson, or maybe I shouldn't give that all away, but how do you think we can bring these things in while we are constrained by a curriculum? Linton.
Well, basically, I think like with agriculture, I introduce my things more practical. Like most of the work, we do our practical, we go out, we use the different tools, and once we use the tools or we come up with we get different solutions, different methods, we try to explore. Even in the same case, like we use certain tools to do the job of another tool. So we actually explore a lot.
So it's not really fixed.
Well, because even on a lesson plan, sometimes you would plan and you never execute your plan.
Right. I understand that.
Yeah.
I quite understand that one. All right, let's see what this video has to offer us. And let me know if you can hear.
Hello, my name is Kevin White, and I'm an assistant professor of science education at the university. Completed my graduate Institute of Technology.
We're not seeing. Are we supposed to have a visual?
Yes.
No, we're not.
No, we're not seeing. I'm not seeing anything.
Your screen sharing is paused.
We can hear, but we're not seeing.
All right, I'm coming. I'm working on that. Share? No. Exit full screen.
Scientist, science teacher, collaborator.
Can you see that screen?
No.
No.
Can you see that now?
No.
Okay.
We're still seeing the screen in the 7 aspects of
Okay, all right. I think I know what it is. I need to kill. All right, I'm coming. I need to kill this. No, that's not on view.
You have to sign when you finish the register.
Sign right. What was the register letter?
All right, can you see that YouTube video now? It still says you.
No, miss.
Where is that? How about now?
Yes.
Okay, all right.
Operations, conceptual change theory and nature of science. I have taught both in private and public schools.
Just checking. Were you able to hear him?
Yes.
All right, then we're good to go. Good to know. So here we go again.
So that's EDSC5410.
My name is Kevin White, and I'm an assistant professor of science education at the University of Texas at
Sorry, remember if you're speaking, you have to mute your mic because it's coming over for everyone. All right, thanks.
We can't hear anything.
We can't hear anything.
Turn sound now.
teacher collaborations.
Thank you.
All right, we're getting this together now. All right, sound and visual. Here we go.
Hello, my name is Kevin White, and I'm an assistant professor of science education at the University of Texas at Arlington. I completed my graduate work in Chicago at the Illinois Institute of Technology. My research focuses on model-based learning science-teacher collaborations, conceptual change theory, and nature of science. I have taught both in private and public schools, grades 5 and 7 through 12. While teaching middle and high school science, I received recognition for my work in bioethics and STEM instruction, or science, technology, engineering, and mathematics instruction. I'd like to take a few moments to tell you about one of my research interests, nature of science. Let's start by asking, what is science? Well, we know it's a body of knowledge. It's the concepts, theories, and laws that make up that body. There's also processes and methods, the ways in which we go about obtaining that body of knowledge. And then finally, there's nature of science, the characteristics of the knowledge, mostly the knowledge that comes about by the fact that we're human beings. There are certain implications and characteristics of the knowledge that we obtain. Currently, the emphasized goals of science education include scientific literacy, and the National Research Council defines that. We also have inquiry as being part of scientific literacy, as promoting an understanding of the scientific endeavor, critical thinking skills, and scientific literacy, and also nature of science. These same bodies identify the fact that it promotes scientific literacy in it.
All right, I'm just going to pause there. Just want to know, do you know the goals of science education in your own countries?
Very good question.
Even if it's or let's make it a little broader. Or how about the goals of education in your country through the Ministry of Education?
I guess to implement knowledge.
Well, I wasn't necessarily saying for you to if you knew of them, you're aware of them, because even the curriculum really should come out of some bigger vision or some bigger goal. Remember last week we looked at the various curricula, and we recognized that there were some social aspects of all the curriculum. So that means that there's some bigger vision or goal that's driving those curriculum. Even for countries, here in Jamaica, we have something called Vision, is it 2030? And we're saying that by the year 2030, Jamaica should be a place where persons would want to live, work, and raise their children and do business. That's the goal. And by 2030, what needs to be done to achieve that goal by 2030 is many things that need to be done. Something obviously in sciences, something with our education, something with our business, how we do business, something about our family, how we treat each other. I mean, it's a multiple task event to get that goal to be achieved in 2030. But when it comes to our educational goals, there's just one little jingle, as Linton had said before, and our jingle is every child can learn, every child must learn. And that drives our education system, that every child can learn, every child must learn. So that's one of their, one of the ways in which they try and capture the goals here. I don't really know our science education goals, but we know what that has been, that jingle that I just shared is something that has been promoted throughout the education system, regardless of what discipline you are in. So that's why I threw that out, that if we kind of had something that was a bigger goal, to realize that everything that we do must fit into that goal, it helps us to identify what we're doing and if we're doing it to meet that target, not just simply on a curriculum level. Because if you notice, this is saying for them at that time, scientific literacy, promoting inquiry, and an understanding of the nature of science, that these three things were goals of their science education. So it's something that we probably need to find out for ourselves in our various countries. What are the goals? And they change. I'm going to show you a clip from the UE strategic plan. Every country has a strategic plan for the various ministries. So even for your own countries, there will be a strategic plan for how they're going to achieve the goals in sciences or in the arts, and you'll find certain things changing over time to meet those goals, usually very long-term goals. Because as I said, for us here in Jamaica, that 2030 vision is, 15 years from now. I'm not quite sure if we're going to make it, but it's interesting that they have a science education goal, and we need to know what it is in our own countries. All right, let's continue.
South. What is nature of science? It typically refers to, a technical definition, let me give you first, is the epistemology of science. Science is a way of knowing, or the values and beliefs inherent to scientific knowledge and its development. Let me give you some examples of what I mean, or aspects of nature of science that might help you understand what I'm talking about a little bit better. There's tentativeness. Scientific knowledge is subject to change. Creativity, because human beings are doing it, it necessarily involves imagination. That there's observations, and these observations lead to inferences. These inferences, going back, are based upon these observations. So distinguishing between those two is important. Subjectivity, that the background, the unique differences between scientists, in part, are the reason why two scientists can look at the same data and yet come to different conclusions. Functions and relationships of theory and law, that, for example, a theory is an explanation, whereas a law is a description, where a theory can never become a law, and a law can never become a theory. Those types of things related to theory and law. Socially and culturally embedded, that science is influenced by society, and society is influenced by science, that two-way interaction. And finally, empirically based, that scientific knowledge is based on our five senses, or extension of our senses, like a telescope or microscope. Now, where I'm going with this is, I would like to share with you where my research is going, is focusing on the intersection of learners. Each of these are knowledge domains. The pedagogy, knowledge of teaching, knowledge of curriculum, of subject matter, of schools, and of learners.
All right, I'm just going to use this diagram even before he goes into it himself. But this is where we are, right? Somehow teachers aren't there. But so we're at our different schools. We have our different learners at our various schools. We're teaching our different subject matter. We have a various curricular driven, that we have to cover. And then pedagogy is a science of teaching, a way to execute, as Samuel had said, the method, how we're going to do this. And we're concerned about this. We're concerned about how can we get our learners in our particular schools with the various administrative pressures, whatever those might be, and constraints, whether you have a science lab, if it's equipped, etc. Then you have the subject matter part coming out of your curriculum that you must cover, and then now to figure out a way, how can I bring it across so that these learners can get it? That's a whole lot of stuff that's going on. Teachers are great jugglers. Do you know that? Hello?
Right. I said, you're
Yes,
right.
we agree. Yes.
Yes, this is a juggling act, and this is just a portion of what we have to deal with. And it's funny, he didn't have teachers there. Strange and oddly enough. But let's see where he was going with this.
The intersection of those is specific to the subject that's being taught. And in this case, looking at science, the pedagogical content knowledge that we're talking about is how do we teach nature of science, the specific strategies, the specific ways we might go about teaching nature of science. So one approach is to be implicit about it. Is by doing science, students will come to understand the nature of science and scientific inquiry, and that was popular in the 60s and 70s. But there are several assumptions. Unfortunately, I don't have time to go through. You can go ahead and pause and take a look at and send me an email if you have any questions about it. But the research does not support the effectiveness of this approach for enhancing conceptions of nature of science and scientific inquiry. So just by doing science students will not necessarily understand nature of science.
Oops. One second.
Should include scientific literacy, being part of scientific literacy, as
I'm just
promoting
going
an
back because I want
understanding
to
of the
pause on
scientific
that,
endeavor, critical
that
thinking skills,
slide.
and scientific literacy, and also give you first development a little bit better. Activity that based upon these same data and yet socially and culturally embedded scope. Research was questions about it.
Okay. No, this is true. In the 60s and in the 70s, you see a lot of literature talking about like science for all. That is out of that era that the concept of science for all came out, where simply doing science, students just engage in a lot of investigations and activities. That was one of the early ways in which they thought that this understanding of what science is about would be communicated to the students. So the same 7 points, or a couple of those points, it was assumed that as students conducted an experiment, did an investigation, try to solve a problem, that in doing that, they would have an understanding of what science is about. But this particular researcher is suggesting that that's an implicit approach and that it didn't necessarily communicate the nature of science, or the students didn't necessarily make the connection. They were just doing a lot of activities. And if we ourselves aren't careful, we can be doing that same approach, an implicit approach to just doing a lot of stuff, but we're not making the connections. For example, let me throw this out. Do you find that sometimes a student will be engaged in one activity, which, as Ava said, you want them to make that transfer to another activity or to something else, a new body of knowledge, having acquired some earlier foundation? Do you find that sometimes the students struggle in making that connection? Anybody at all?
Yes, they do. They do.
Most of the time.
Right. So it means that something isn't there to support their thinking. Something is missing. There's a missing glue or connector, because we see it as teachers. We understand where the content is going and where it's coming from. But the students are not making the connection as smoothly. And in this course, we wanted to look at, is it possible that in our classroom, that social environment that exists, is it possible that we ourselves are acting as a barrier in communicating our content or skills, because we have not communicated to our students what it really means to do science of any form, whether it be chemistry, physics, math? If they understood that and we're going to look at that they are part of a body of scientists, and that they must know how to communicate their information, to speak about their information, because the information is tentative, it's subjective, that they have to make accurate observations. If they understood that, maybe as they do the new body of knowledge, new topics, hopefully maybe it can provide a kind of support for them to transfer knowledge. But that is something that you can try out for yourselves. After we have done this, try and see if can I really somehow just take one of those aspects of the nature of science, and maybe over a period of weeks, just introduce it little by little, keep reinforcing it, and will it provide that kind of glue that would help them to transfer one knowledge to a new situation? But let's continue.
But the research does not support the effectiveness of this approach for enhancing conceptions of nature, science, and scientific inquiry. So just by doing science students will not necessarily understand nature of science. Another approach is using history of science to teach about nature of science and scientific inquiry. Historical approach, what does the research say? Well, it often assumes that present beliefs have resulted from a linear logical progression from past beliefs, which is not necessarily the case in the history of science. Students often develop the impression that past beliefs and scientists were simply uninformed and ignorant, which again is not the case.
Oh.
So what else does the research say? It says that it's virtually impossible for students to suspend prior beliefs during a role play activity, for example, if they're studying the history of science. And it has demonstrated only moderate success when the focus has been on the tentative, creative, subjective aspects of nature of science. And finally, it has not been effective with respect to understandings of scientific inquiry, something else we could talk about. So
let's pause here again. Has anybody ever seen this being used though, teaching the history of science? Is it in anybody's curriculum?
Jason from Rita, not in my teaching personally, but when I was in university, they taught us something about the history of science.
Mm-hmm. But does it occur anybody at all? Thanks, Jason. Does it occur at the secondary level any at all for anybody? Does it come up in any?
No.
No, not really.
No.
The only aspect that may come in is under the topic of mitosis and meiosis.
With Mendel.
That's the only area that I've seen it. Outside of that, there's nothing much on the history of science.
Right. It's true. I have never heard of that being introduced anywhere at all. All right. Well, according to this researcher, even that approach doesn't seem to communicate effectively what science is about.
Let's focus on nature of science. The explicit approach. This treats the understanding of nature of science and scientific inquiry as a cognitive outcome, not a byproduct. The goal of improving students' views is planned for, taught, and assessed. That instruction is geared toward various aspects of nature of science or scientific inquiry and utilizes elements from the history and philosophy of science. And it encourages reflection that connects aspects of the nature of science and scientific inquiry to the classroom activities and the activities of scientists. This is talking about the explicit approach, could also be talking explicitly about aspects of nature of science while coupled with the history of science. So the key here, distinguishing between these three approaches, is that teachers elicit from students responses that demonstrate their understanding of particular aspects of nature of science. And in the beginning, teachers are guiding students towards identifying those aspects during their own inquiries or during reflections on the history and philosophy relevant aspects that they've been studying in class. And research consistently supports this effectiveness. Research on nature of science and scientific inquiry. A few generalizations can be made. Students do not typically possess adequate conceptions of nature of science. K-12 teachers do not typically possess adequate conception.
Let me just go back to that. One more. And we can attest to this, that we ourselves weren't even too sure of this nature of science. It was never communicated to us. It was never, as Ava said, that we teach the way we have been taught, and we didn't see that kind of approach being used at all. It was always about the content, getting the content, acquiring certain scientific process skills, how to observe, how to measure. But certainly Here it's identifying that students don't understand it, and teachers typically that we don't have an adequate understanding of
Well,
what that
teachers
is.
do not typically possess adequate conceptions of nature of science. Conceptions of nature of science and scientific inquiry are best learned through explicit instructional attention as opposed to implicitly through experiences with doing science. Two more here. Teachers' conceptions of nature of science and scientific inquiry are not automatically and necessarily translated into classroom practice. And finally, teachers do not regard understandings of nature of science and scientific inquiry as an instructional outcome with status equal to that of traditional subject matter.
All right, okay. So what he's saying in this very last part, that's a challenge to us as we are almost, 2/3 through today's class. This is a challenge that I want us all to get, that we need. It says teachers do not regard understandings of the nature of science and scientific inquiry as an instructional outcome that is equal to any other outcome that we want. So if we want our students to know how to titrate, if we want our students to know what the Mendelian laws are, if we want our students to know what husbandry is, they're saying that just like how we plan for those outcomes, cognitive, whether they be or social, where you want them to work in a group, cooperatively, respecting each other's views, whatever. Here's a challenge. The challenge is that we somehow need to infuse in our instructional approaches, in our methods, in our lesson plans, something that deals with the nature of science as a learning outcome. So if it's to say at the end of this lesson, students must be able to, and then you list your traditional subject matter outcomes, they must be able to titrate, they must be able to know the volume, they must be able to determine what the parents are, if the offsprings are so and so. And then somewhere in there, you should have something that deals with any aspect of the nature of science. At the end of this lesson, students should be able to understand the difference between an observation and an inference. Or students should be able to understand that science is subjective, but you plan it. And that's what they're saying. And I hear Samuel's cry, and I hear Kamisha's cry, I hear all your cries about the curriculum, and it's squeezing us in and boxing us in. But would it really be that hard to really infuse any one of those aspects of the nature of science? I want to finish the video here. Would it really be, what did I just do? I know. Can you still see and hear me?
Yes.
Yes, we can.
Yes.
Right. I exited big time out of that. But is it really that difficult for us to infuse any one of those aspects of the nature of science in our lessons? So I know that was a whole lot that we just went through. So here's going to be the task that I'm going to give you to try and break this, my voice and this setting that we have in our class. You are going to identify in your subject groups any topic, agree on something that you can both, come to a consensus, even if you don't teach the same subject. And I'm going to put up back the listing of the different aspects of the nature of science. So think of a lesson, a simple lesson with at least one other objective, but also add an objective of the nature of science. And how would you bring that in? So I'm going to put you in some little groups now. How am I going to group you now? What's the kind of mix you across? I know that the St. Lucians are doing agricultural science, but I want to kind of break you up. When can you communicate with each other without everybody else hearing when you all speak? Is that possible?
No.
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 No. Yvette's laughing at me. All right. I hear you. All right. I'm going to fix this. All right, not today. All right. St. Lucia, as a peer, just come to a consensus of a topic and come up with two objectives. One, a regular learning outcome. Another, one that will address the nature of science that you think can be executed in a 20. How long are your teaching sessions?
40 minutes.
40
In Dominican
Single period.
50.
All right. Dominic,
Single.
40 minutes. St. Lucia,
40.
30. I know that my Bermuda.
Dominica,
How long? I know
Dominica is 50, 50.
50 for a single session.
Yeah.
That's a
Yes.
long time.
That's a long time.
Wow.
Wow.
Yes.
Do you have double sessions?
No, we
Oh,
don't.
okay.
Oh, that sorted that. All right. So same instruction to you, Dominica. But Samuel is a physicist and you are chemistry, right, Kamisha, or biology?
Yes.
Oh, so you have to come up with a common discipline that you can relate to. Again, identify one objective, a learning outcome, plus another one from the nature of science that you think you can explicitly teach. So my Bermudan colleagues, similarly, so I want to work as one big. So maybe Mason, you're sitting next to Tracy.
Like, our objective might not be something too difficult to come.
Yeah, go ahead. I'll help you.
All right. So Jason and Tracy can work together, while Ashley and Vanessa, since you're on the same bench, can work together. So Ashley and Vanessa, genetics and nutrition. I don't know how you're going to work that one out. But Tracy and Jason, you can come up with some topic from biology. Everybody there?
Yes.
All right. So I'm going to
Yes,
put
we
up.
are.
All right. So I'm going to put up back the nature, the tenets or the aspects from the nature of science. Just give me one moment. Where? All right, so there they are. I'm giving you 15 minutes on the clock for this one because I really want to hear how you're going to, translate this or communicate it to your students.
So we have to use both of our subjects to get this across?
Just one of them.
Or just one?
Something where we can combine the two.
What's your degree?
I know nothing about nutrition. Anything about genetics because
DNA. So what? I'm
Well,
sorry.
they do
I have trouble
chromatography and biology now. They do
the acronyms.
Oh yeah, I guess I am.
the cooling we need to get
Creative.
one thing from spinach nutritional then it could be
Being creative or being.
Oh well, that's.
yeah, one of
I don't know
them is
why
7
this is.
points plus 1. So I'm trying to teach Mendelian inheritance, but
for chromatography.
observation versus Mendelian inheritance and observation versus inference, they go together. But if we don't know Mendelian inheritance, that's not going to work.
Right.
You got the chromatography that they do that's chromatography for fun, teaching the skill of the year 7 and I just have to do
Right. That's what I was reading. But it's not.
so we can chromatography for this.
It's a method of identifying different substances. Separate them into. Like, I mean, it's measuring how fast. Different substances go at different, yeah, sizes and different speeds, but being right but this would be one.
You know what I mean? We're getting creative here. Very good. We stick to the radio label, you know, as did I say? I don't know.
Methodology. Oh, I think we just asked for that.
So does it, guys, when you have something moving through paper, we did chromatography, what do you do? It's not
Like the
distillation,
process
it's
by
not
which it moves
diffusion,
through the
is it
paper.
diffraction,
Isn't
You separate based on size of molecule. Hang on.
see,
Diffraction is light. Yeah.
yeah.
To diffuse it, just spread it out. Small. Chromatography is diffusion based on size of molecule.
Okay, so I'm just,
it is also fine expression.
yeah,
So
Empirically based. That's what you're experiencing how it's made of separate things.
I remember reading about this a little bit, what you're saying, like, you know what I mean? Like they talk about the flowers and stuff like that. Yeah, you have, so I take a white flower and a blue flower.
You can do that one along with
The observation in one purple.
The observation.
If I wanted to search, I don't know. See if I can strategic plan. You cannot connect to the internet.
This person.
Why? Was the battery is low? You know, for when it's like obtaining IP address. Oh, I'm thinking I can't get onto the internet. Yes, it's there. This phone was ringing. Yeah. 0339. I know that number. Yeah, hi Tasha, you're calling me?
Is that like socially and culturally?
4 times an accident.
Yeah.
People my way.
Yeah. Once it goes to voicemail, credit is gone. All right. Eh?
You know, in some places in some parts of the world, have
One word to describe them. I never even knew that. I thought it was a regular $2 per something. You
know what I mean? That's so cool.
How would you put that into your?
If I wanted to look up something on the UE website, can I look it up without or once on the screen? Once the screen changes.
Well, it should be able to look it up without where to stop share.
Just stop.
Or whatever you're doing on it, restart it.
I see what you're saying. See if I can download it on my phone and then.
May not affect the nutritional value, but it may affect.
Kind of going like
I know exactly what I guess that's why we're taking.
Yeah.
Before we scan one minus. So what are we gonna say about these tomatoes? Just keep them out to the same. Okay, so which one are we still looking at this here?
Got 2 already, so.
Really?
Pretty base. I know. I'm just thinking like, could it work?
Okay, that's nice. That's nice.
Should I just assume that everybody is I don't know how that would
What is that?
fit into your career.
The nature of the
Oh.
Socially embedded.
Yeah.
I'll let you know copy that.
Thanks.
Anything else regarding this?
Any of them getting anything out of the course? Like teach a course where almost hard for them to get out the course. It's all up to them. Only they can take into action. I will try and encourage them.
Different person may say that this one.
Already done?
Oh, this is a page. Page 24 of the US strategic plan.
It may look very similar.
This person.
So you say if I were to
This one is okay.
is anyway, I don't think I'm seeing it.
Oh,
What's it?
they think that one looks like that.
Please. Oh, that was just to indicate that this is not being seen by them.
I like
We can do the other ones. You need to ask her.
I would have to say share. Where did I just see? How much?
Oh, so we have to figure out the experiment that we're going to create?
No, they're going to be creative. They're going to come up with an experiment design. I'm forgetting people to teach them this. It's actually probably more equal than you're sending them on a 10-mile run.
10 miles, they need to brand that we can really see how this is going to affect them versus not affect them.
At the speed that I run, that would be the entire class.
Well, okay, well, we have to have a really, really tight, like, controlled situation.
Just checking in with you guys. I hear some of the conversations. Everything going all right?
Yes.
It is.
You might want to define all right.
I hear of a 10-mile run in Bermuda.
That's actually trying to kill our students.
How many more minutes do you think you guys need? Maybe 5 more minutes?
We're actually done.
All right.
We're done with this. Tracy just, I think she went to the restroom, so it's when she gets back.
All right. How are we, Samuel and Kamisha?
So we're ready.
Ready.
All right then. All right. So when Tracy comes, Vanessa. All right.
I was going to go with that.
Okay. Now, I always like to start not with the task, but the process of the task. I always like to, what they call it, debrief. So, how was the process for you, Samuel and Kamisha? Just the going through, not the actual, final thing which you're going to share, but what was the process like for you?
Yeah, it's very easy.
All right. You hear Kamisha?
Yeah.
All right. How about our Bermudan colleagues? What was the process like? What was what was it like having to collaborate and to address this thing?
Our biggest problem was the lack of crossover between genetics and nutrition.
I can imagine.
Crossover.
All right, got that one. All right, how about St. Lucia?
Um, very easy process because both of us are agricultural science teachers, so it was okay.
All right then.
Luckily for us.
Right, right. All right, yeah, the common platform. All right,
Yes.
let's start with Bermuda. Anybody with any of the two groups would like to just share what was your topic and what were your objectives and how did you work out how you would achieve them?
You didn't call him?
So our Jason and Tracy.
Well, yeah, I think I'll have to do that.
Yes, okay, go ahead, Jason and Tracy.
Yeah. Okay, so we're dealing with the year 7 class, right? It's like 12 to 13-year-olds, and we're doing an experiment which is chromatography. And the objectives of the experiment for the lesson, I guess, is to uh, for the kids to learn about the fusion.
Go again.
The objective of the lesson is for the kids to learn about diffusion.
Okay.
That's like the content, scientific content, and also to follow instructions. And I guess we can go on with that. But then our nature of science objectives that we want them to learn about, well, one is subjectivity versus, one observation. Okay, so
Observation versus inference.
yeah, and so like I guess just to explain what chromatography is or whatever what we mean by that is we have
What we do with Jason is we do a murder mystery with our year 7s, and I put a mark on a piece of chromatography paper, and we tell them that one of the teachers has murdered the head of school, and there was a note found at the crime scene, and then we give the kids a bunch of pens.
I'm here for just it's after 7, just remember.
And then after the crime,
I'm just reminding you.
they have to say which pen belonged to the murderer.
Oh, okay.
So there's like I put the original dot on the chromatography, and then they put 6 other pens.
What are you looking for?
Sorry, one Tracy. Remember, everybody, when you're having conversations, we can hear you.
Just put in the email address and it should come up.
Sorry, St. Lucia. Remember, once you're having conversations, you need to turn the mic off, or right, because we're hearing you. Sorry about that. Yes, Tracy. So they all have to figure out which pen is the murder weapon.
Yes, and therefore the pens are named with teachers' names. So they're all different black ink pens. So they all have different patterns when they go through the chromatography process.
Okay.
And so how that relates to observation versus inference is because they're doing observation by looking at the different lengths of ink on the chromatography paper.
Right.
And we have inference about which pen is the same as the original pen, the murderer's pen.
Okay. All right. Very good. Now, obviously, that lesson is something that's doable. They've done it before. That's what you're saying, Tracy. That's something that they do.
Yes.
Right. But just that now we want to make that connection very obvious that they're not just doing. Remember, the idea about teaching the nature of science is not just simply them doing the activity. Yes, they're obviously making observation. Yes, they're obviously making inference, but that we bring it to their attention that this is what they are doing. Very good, very good.
Right.
All right.
We also
sorry.
I don't want to take up all the time, but we also tried to include some other aspects.
Sure.
Like subjectivity.
All right.
We would say that okay, one person may look at the murderer's pen and look at the other pens, and one person might say that one pen is the same as the murderer's pen, but another person may subjectively say that another pen looks like. Maybe some of the pens are similar, which could be leave up to subjective interpretation.
Right. Okay.
So, And again, we'd explicitly talk about that, you know, saying that this is possible, it can happen.
All right. Great. Thank you. Oh, sorry.
One more thing. I had a question about this social and culturally embedded. I was wondering if this would be that, if you could explain it. But I was thinking like we could say, we're assuming that everybody knows what a pen is in ink. I mean, like in certain parts of the world, they may not have pens, they may use pencils, or you know, their teacher may just only have chalk, they may not have pens. So maybe there's a statistic about that or something that we can include in the lesson and present to them to say that this experiment makes sense to us culturally because we have these things, but in other cultures they may not have them. Would that be
Right.
relevant?
Right. Good point. Good point. And so you're bringing right away that even though things that they might take for granted, it might not be so in another cultural setting.
Right.
Very good. All right. So you actually addressed 3 aspects of the nature of science in one lesson. In one lesson. All right. Okay, great. All right. So let's go quickly to Vanessa and Ashley. I don't know how the genetics and the nutritionists met at the intersection, but let's see how they work that one out.
In an act of pure desperation, genetically modified organisms.
GMO.
We would do a lesson on how fish genes have been spliced into commercially grown tomatoes so that they're more frost resistant. They've spliced in genes for antifreeze. And then we would ask the students to design an experiment, so you've got creativity, to determine if these alterations would actually have any difference to the nutritional value of the tomato.
Right.
So they would have to creatively design an experiment, but it would also need to be empirical. So they'd need to actually, they wouldn't have to actually do the experiment because I don't know quite how you determine if tomatoes have been genetically modified. They don't exactly label them.
Right.
In theory, to theoretically to design an experiment where you could actually determine if this affects the nutrition of the tomato.
Mm-hmm. Yeah, that one's going to be a tricky one for the outcome, the final outcome.
Well, I don't actually know what the outcome of that would be. I don't think it affects the nutritional value, but I don't know.
But at the same time, yes, go ahead.
If we didn't if we didn't make them create experiments to determine the nutritional value, then we could observe the effects of ingesting GMOs over some period of time. We don't have enough time to do that in high school, but you know, we're trying to pull at strings here on how to create something.
Right.
The topic that you've given us.
If it had been just genetics or just nutrition, we both could have focused.
I understand. But that's similar to something that's done in the CXC exams or for the SBAs called planning and designing. So they never ever get to execute. They just plan, design the experiment, and kind of propose what an outcome could be like. So you're really calling upon just the same two aspects, really, the same creativity, because they have to think about it and design something of their own that could address a phenomenon that's being observed, but they never execute. They never get to execute it. But based on what they already know, and as you're seeing there, what they know about genetics already and nutrition, they could make an inference that doesn't, but not based on an observation that they're literally making. You understand what I'm saying?
Yes.
So that particular exercise, planning and designing, which is, you know, as I said, for the Caribbean Examination Council, that is really designed to pull that aspect out of students, where they can be creative, make these inferences even though they don't have final data to really support what their inferences. So the inference is not based on observation of real data, but it's really based on a theoretical foundation, which is important for students to be able to do that. In other words, they're projecting. They're able to say what could have happened, and that's an important aspect of being able to handle information, whether it be scientific or otherwise, frankly speaking. To be able to forecast what would happen if, and not many students can think through that. Not many adults even, because the most persons, they leap and then, what's the expression? Look before you leap. They leap and then look after. But what you are bringing out is very important for students to be able to do that. Are they hearing me? Okay, thank you very much. That one was a very interesting one. All right, so let's hear from our agriculturalists now, our agricultural science teachers. What collaboration they came up?
Okay, well, basically it was a little easier for us because we both do agriculture. And the topic that we were looking at, no, first of all, we were looking at our topic as soil.
Okay.
Okay, and then in our topic, we came up with our objectives. One, what soil is. We looked at the soil, the types of soil, composition of soil, functions of soils, and identify soil structure and soil texture. Okay, we follow?
Yes, wonderful.
Okay, all right. Then we went into the content. We said that soil is the outermost layer of the Earth's crust. It is also a medium for plant growth, and it's a habitat for plant roots and soil microorganisms.
Micro and macro.
Yeah, micro and macroorganisms. In that, we discuss the types of soil, where we look at loam, clay, silt, and sand. And under the composition, we look at it is made up of 25% water, 25% air, 45% mineral based on the parent material, and organic matter, which is 5%, which is the decay of plants and animals.
Yes. A point to note is that the water percentages, we will explain to the students that the water percentage will vary based on the prevailing conditions. But it's a drought, it's rainy season, that is not permanent, it's just changed with the conditions at the time.
Okay, and after we looked at the functions, for example, we have one, it would keep the plant upright. It contains minerals for the plant roots, or even serve as for food. It supplies air and water to the plants for plants use, and also as a habitat for soil organisms. And in our materials, we look at different soil samples, like we look at free soil samples. And we use a beaker and also water to actually carry out an activity where the students will grab some soil sample and add water to form a mixture. And depending on the feel of that soil, they will be able to identify the different soil types. After this, we'll do a follow-up activity where they would walk into the garden and identify different soil types that is found in the school garden. And at the end, we'll carry out an evaluation to identify soil types based on the texture or the feel of the soil. Yeah.
Okay. All right. So what aspects of the nature of science were you explicitly targeting?
Observation, inferences, and subjectivity, I think. These two are paramount. Yes. That's what we did.
Okay. And how would you bring this to the students' attention? I mean, the activities are great, but how would you bring it to the students' attention based on what we are discussing here? That we want them to know that these things are, important aspects of science. So another time, again, when you do another activity, they would have, understood this observation, inference, subjectivity. How would you have brought that across?
Well, based on the activity that we did, where they grabbed the soil sample, that would show them that they have to do observation to actually detect, well, and okay, that is a sandy soil or it is a clay soil.
And then they'll be able to make the inferences when they actually go out into the garden and said, okay, based on what we did in the lab, what do you think that soil type is, etc., etc., etc.
Right. Okay. All right then. And the subjectivity would be based on if it didn't quite work.
Exactly.
Right.
They didn't quite identify the some person might say this is a sand, this is a clay or loam, and then based on how you feel and stuff like that. Yeah.
Right. And so at each point, according to that researcher, he's just saying that as you go through the activities, be very clear in your actual, just like how you would teach to say, okay, this is the shoot of the plant, these are the leaves, the lower surface has more stomata than the upper surface. He's saying that just as how you would do that, drawing and being very clear with your content, that you should be just as clear with these, aspects of, or the characteristics of the nature of science. So that's a very good one, because you have three things going on. Well, two points coming out: understanding what it means to make an observation and make an inference, but you tell them that. And likewise the subjectivity, because yes, I remember doing experiments like that, and sometimes I'm feeling this soil and trying to figure out, okay, is it silky or is it sticky, or is it, so that was a nice one to bring that out. And I want to just stick up a pin here to recognize that not necessarily every single topic you're going to look to put this in, but certainly topics that lend itself to it, then go for it. Everybody got that?
Yes.
Can I ask a question?
Sure, Eva.
In your lesson planning, when you have already explained to the students the nature of science in terms of the 7 that you have on the 10 tenants that you have, can you actually have them, after you finish the lesson, with like a rubric or something, and have them identify what is it that they have done to see if they have understood the nature of science? Can you do that?
I think that's a beautiful idea, because in fact, remember he said that anything that you teach, well, I don't know if he said it, but certainly you might have heard the expression, assessment drives learning. If there's something you want your students to learn, you must assess. You must assess it. Don't leave it up to oh, I mentioned it so they know it. I've said it so they know it. So that's a very key point that you're making, that the only way really to determine or to measure the extent to which they have acquired or understood or appreciated something, intervention that you have made, is to assess it. So that's quite fine. And I wouldn't give all 7 of them one time. I would do probably just 1 or 2 at a time. Assess 1 or 2 at a time. Assess 1 or 2 at a time. And over a period maybe of a term, I would have probably addressed them, 5 or 6 of them over a term. Notice I'm not trying to say that you're going to teach all this in one class, because it's going to be ongoing. It's going to be ongoing. So you can introduce it and then say, next class, I want you to look at what is the difference between an observation and inference. Then maybe the next class, having introduced it, got them used to it, you give a rubric and say, okay, having done this exercise, which one of the do you think this was referring to? I think that's a beautiful idea. Just creating a rubric, very gently assessing for it. I mean, and at the same time determining if they've understood it. How does that sound to Dominica and Bermuda, that suggestion from Eva?
Yeah, that's very good.
It sounds good.
Yeah, a wonderful way, because you're correct. I think the gentleman did say, and I mean, it's not. I'm not just saying what he said, but it's known for anything you teach, and you want students to make note of it beyond just having made a comment, is that you have to assess for it. You have to determine the extent to which they've acquired a new knowledge or a new skill or a new way of thinking. Excellent. All right, let's bring in our, sorry. So Ava, yes, I just want to say that was a good idea, a good suggestion. And so I'm looking forward to hearing the feedback from you on when you implement it in your class. Did Ava raise her eyebrows?
No, I didn't. No, I didn't.
I'm just teasing you. All right, yes. So Samuel and Kamisha.
Okay, our topic is on nutrition, and the objectives are students should be able to test for starch. They should be able to differentiate the color change that occurs between a food sample that contains starch and one that does not. And thirdly, differentiate between observation and inference. Okay, so what they are to do in this session is to test different food samples by using iodine for starch. And if the food sample contains starch, then to turn a blue-black color. And the samples that do not contain starch will not have any color change. So then at the end of the activity, they were to differentiate between observation and inference by saying what they observed between the food samples that contained and did not contain starch, and then inferring that the food samples which had the color change contained starch, while the food samples which had no color change did not contain starch.
Right.
That's it.
That's it. And and that I find, and persons had already said it, those who are actively teaching, it's a very critical skill, observation versus inference. And we have all shared that we do find our students struggle with that. So this was I noticed that for the groups, that was one aspect that all groups shared, decided to go on to talk about, because it's so important in our science teaching, and students really sometimes mess that part up. They've made the observation, but they cannot explain, or account for their observation. Thank you very much. Thank you very much. That was a very rich for me. Don't know how you found it, but I found that was a very good. Because you see, why was it rich for me? You were just introduced to this idea. You already knew about it anyway, but just never had these terminologies about the nature of science and stuff. You were doing it all along, and within less than 15 minutes, you are able to think about it and bring it to a lesson that you were just forced to present now. And I would really like to encourage us that for these classes to really be of benefit, for you to reap fruits from these classes, is to put them into action as soon as you can. Implement one thing and test it. Test it over time. I'm not necessarily saying that you're going to see something right away. Just like if you plant a tree, you have to water it, fertilize it, tend it, prune it, make sure that it's free of all weeds and debris, etc., etc. So similarly, even this idea today that we have looked at and explored, what is the nature of science? How do students view science? What is our own view of science? And what are we doing about it? Do we really actively present it in our lessons? On the PowerPoint that I had sent earlier, I'd asked that question. Do you infuse the teaching of the nature of science in your lessons? Why or why not? And we had explored that already. We understood the chains, so to speak, of the curriculum. But here, as I said, less than 15 minutes, you were able to really come up with a simple lesson, things that you're familiar with, because this course is not about trying to teach you how to teach you the content. You have that already down pat. It's how to ensure that as you communicate the content, that you're aware of some things that affect your classroom socially, and just an understanding of how students view science, the very content that is so, endearing to you. You love genetics. You are, head over heels with your chemistry and your physics and your biology. But if you're the only one head over heels, then you're going to have a warm time convincing your students of what you're teaching. Okay, so what do you think of what we have discussed so far? Relevance, impact, anything that you can take away, carry forward, throw away, put in file 13.
Well, so far it has been very informative, and I've observed that though we may not have known about the nature of science and so forth, that some of the aspects under that subject can be easily implemented into our lesson plans.
And is that coming from Kamisha?
Unfortunately.
I wouldn't say unfortunately. I would say, wow. Because sometimes I understand. Sometimes things really look like what more are they giving us? Don't they know that we have SBAs to mark? Don't they know that we have 50 students in the class? Don't they know that these students are poor readers? So we have to teach them to read. Don't they know, I mean, the list goes on and on and on and on. But I'm not asking you to make major changes. It's just to look at it, think about it, reflect on it. How can I introduce even one aspect of this in a lesson coming up in the next month or so? It's really looking from that angle. And again, for this course, what I love about this course is the opportunity for me as a practitioner to reflect on that practice. So at the end of this, hopefully we can look and say, because even for me, I'm looking at it for myself as well, saying that, boy, in my fourth form, where we just dive into the content, we are making sure that those SB school-based assessment reports are ready for March when, CXCs will be collecting. And because of that pressure, it's easy to ignore these things, but they're so important because they help to build the full scientist in the person, your science student, my science student. Anybody else? Anything you want to put in 513 will never work. No, this is just as usual, another theory that has no place in the classroom. These people just sit down and just think of these ideas to make our lives miserable. Nobody? All right. 2 more points and we'll be out of here. And this that I've put up is what is called UE strategic plan. It's dated or outdated, 2007, 2012. But the reason I'm bringing this up is to show you how, remember, talk about goals and visions. UE decided in 2007 that over I think this was formulated in 2006. But the idea was that between 2007 to 2012, a 5-year period, they wanted to accomplish this. They wanted the graduates, all UE students, to be career ready, well grounded in their disciplines, articulate, and possess superior problem solving and critical thinking skills. They wanted them to be socially conscious, regionally responsive, well rounded, committed to ethical behavior, globally attuned, and to be able to work in a team as well as independently. Now, they created a vision of what the graduate should look like. And similarly, I want to encourage you to create a vision of what your student should look like. What should a student of agricultural science grade 10 look like after my intervention of teaching after 1 term? What should my chemistry student of grade 9 look like at the end of my intervention at the end of a year? Because if we don't have these visions or these goals, yeah, we can be teaching the curriculum. Yes, we can cover the content, but can I tell you, we can end up being the only ones covering the content, and we would have not impacted our students. If I were to revise what person said about what science meant to them, Ava spoke about real, let me put on my glasses, real and imaginative, uncovering the covered. So she's referring to there's a mystery and she wants it for her. It's the discovery of that mystery that's important. Linton said science is fun. It's about the investigations and the experiments. Samuel spoke about infusing science in everyday life. He spoke about the chalk and the carbonic acid and the calcium carbonate, and he made that analogy. Kamisha, science is life. Vanessa, science can improve. No, it wasn't Vanessa. Tracy. No, Ashley. Somebody. Science can improve the well-being of all living creatures. Again, Ashley spoke about the everyday life. Tracy, questions get answered. Jason, helping others to improve the quality of life. If these are such highly esteemed goals, and you want your students to appreciate these things, you want your students to see these, you want to see them to see the fun, the imaginative becoming real, the well-being of life. So we need to be conscious that as much as I have a curriculum, yes, that guides my content, I can't enter into a classroom with just content under my belt. There must be something more that I can give my students that would make a connection with them beyond just the content. Because let's face it, they can go home, as somebody said, Google, cut and paste, and they have content. But they don't know how to apply the content. They don't know the relevance of the content. They can't see that content in anything but miss homework and sir coursework. If you ever hear them talk about it, right? That's a miss homework, or sir, I finished your work. They don't own it. They have not taken it on as their own. So we want, even in this second lesson that we did today, about the nature of science, the fundamentals, the basics, the things that support the content. Because basically that's what this is. All these things support the content. We want to be able to teach them not by the wayside, like the sower, when in the Bible. We don't want them to fall by the wayside. We want it to be very explicit. We want to be clear. We want it to be upfront and personal, up in their faces, that this is all a part of science. And if we can get it from as early as possible out there, it will help the headaches of those who have them when they're about to exit and they still, are, as Samuel said, trying to falsify results, where they're trying to copy or borrow results from someone else because they can't interpret and come up with possible solutions of the observations that they are making. And I think that's about it. Any comments before I just give you a sneak preview of next week's class? Any final comments? Nope, you're all waiting to go out. All right, no problem. This is where we're going next week. In border crossing, where we're talking about social algebra classroom, what are the dynamics that occur between us and the students, between the students and themselves, between students and our content. What's happening in that interaction? I've sent you, for those who have not yet seen their emails, what I did send was a PowerPoint of today's presentation, but I'm going to resend it because I made some updates. So bear with me, I'm going to resend today's PowerPoint presentation because I added some things, just around 3 slides. But I did send the journal article by Letterman that spoke about teachers' views, and it's really very interesting. Spend some time over the next week just reading it. It talks about teachers who are new to the task, how they viewed science, spoke about teachers who are teaching for 9-10 years and how they interacted with their students. And there was another article as well, like a smaller article. So please bear that in mind, just so that you can refresh yourself, your memory of today's class. So you'll have a PowerPoint presentation on your way before the weekend, the revised version of this, and you already have been sent 2 journal articles to support today's class. All right. Well, I thank you very much. I don't know if there is anything anyone wants to say before we head out.
Yes. Ava here again. Will we be getting any information about the crossing before the next class?
Yes, you certainly will. That one, I probably even send it to Miss Mills by tomorrow so that you can get it for the weekend. I'm really trying to get the information out for the weekend. I know. It's especially if you're working and studying, there isn't really any much chance for you to absorb the information prior to classes if it's just on the day. So yes, forgive me, I'm working on that to try and get them out at least by the weekend so that you can have it by then. Good point.
Thank you very much.
I keep it.
Thank you.
I was going to ask you to talk last time about having a break, but we hadn't really discussed that any further.
Yes. It seemed as if you're all seeing fair. I didn't hear anybody make any, okay, can we have the break now? I don't have a problem with somebody saying, can we have the break now? Please, you know. So when you can tell me when you're ready for the break, are we, based on the 2 classes so far, what time do you think is a critical point of about to fall over from sleep or boredom or hunger?
7:45.
7.
What?
7:40.
That's almost end of the class.
When the class is over. What time are you talking, Ashley?
Bermuda time.
Ah, so you're really talking 5:45?
Yes.
At 5:45?
5:30.
All right. Okay, so can we have a consensus? Well, halfway through the class.
Yeah.
Yes.
Yeah.
All right. Wonderful.
Yes, that's okay.
All right. All right then. Thank you. You've been good sports.
Okay, good night.
Bye.
Okay, bye.
Okay, bye.
Ta-ta.